Welcome to all my dear students. I hope you are doing well in your life and motivated enough towards your dream. If not, then don't worry. Just make sure your each day count with your dedication and commitment. So all rewards from this beautiful life are awaiting you ahead for sure. Don't ever give up. Okay, my all beloved civil engineers, we are made to fight and grab success. So make sure you are working hard. And now let's come to learn our very first unit of fluid mechanics, which is fluid properties. Okay. So as I said earlier in my last video, if you haven't watched it, then please go to watch it first, as it was my fluid mechanics introductory video which I made, and then come again here. So let's start it. So first is control volume approach. Okay, control volume approach means it distinguishes between two approaches, which is first one is Lagrangian approaches and second one is Eulerian approaches. So Eulerian approaches is enhanced version of previous approach. What I did, I took two sections. So two constraint boundary, okay, to control the volume. So here in control volume approach, matter is vary and boundary condition is fixed, which is we studied in our last syllabus part video. Okay. So Euler's again say further, um, between molecules there is certain gap, there is certain space. So if we ignore the gap between molecules and consider as one unit, then Euler's call it as fluid continuum. And why I am going to teach you regarding fluid continuum and very much emphasis is on this control volume approach, because I wanted to reach that fluid continuum assumption. It is most fundamental and most important and basic assumptions while we about to start our fluid mechanics journey. So, okay, so what is fluid continuum? If we ignore the gap between molecules and consider as one unit, so then we call it as fluid continuum. So let's jump into our very next headline, which is fluid properties. So here is again very much basic and kind of similar properties we are going to discuss. First one is density. We will denote it as uh, rho. Okay, so rho is mass divided by volume, and rho has, or density has, some standard fluid. Like in liquid, we use water as a standard fluid, and in gas, we use air as a standard fluid. So you can see how much difference in density of water and air. So standard liquid, which is water having density of 1000 kg per meter cube, and air having density of only 1.2 kg per meter cube. So after standard fluid, we will look into units. So units of density is kg per meter cube, and gram per cc is CGS unit. Kg per meter cube is our MKS, or you can call it as SI unit. So basically, if it is not related to our syllabus, but if I'm taking you to some usefulness of these units, then MKS and SI units are generally we use as a engineering, as in engineering, and then some of physicists might be used in at their very beginning to their study. And CGS is not as commonly used right now, but some theoretical physicists are, there is a chances, there is a possibility they are using this CGS unit. After density, after density, there is one again density we have to study, which is weight density. We call it as a unit weight also, or a specific weight too. And our formula, which is weight by volume. Here is also we use water as a standard liquid. So weight density of water is 9.81 kilonewton per meter cube, and weight density of mercury is 13.6 kilonewton per meter cube. Why I'm writing here mercury? Because mercury is used as like barometric and manometric fluid, which we will further discuss. Okay. So weight density denoted by gamma. Then third one is our specific gravity. Before going to into specific gravity, I have to show one relationship between, important relationship between the two densities. So our first density is mass density, which is mass by volume, and second one is weight density, which is weight by volume, and they both collaborated with weight density is equal to rho into g. Weight density is equal to mass density into gravitational acceleration. Okay, so you have to remember this relationship between them. It is most important. So after that, we are heading towards specific gravity. Specific gravity is nothing but to relative density. Okay, so which density we use? First one in numerator, there is a density of given fluid, and in denominator we use density of standard fluid. So formula become density of that particular liquid divided by density of standard liquid, which is generally we use as water. If they mention standard fluid is something else than water, then you have to taking into consideration of that given liquid. Okay, so specific gravity is very much simple, and specific gravity is a term which we will use further in soil mechanics, in environmental engineering. So it is most useful, but easy to understand, isn't it? So after specific gravity, we are heading towards viscosity. But just actually going too deep into viscosity, let's just briefly understand what is friction and what are the frictions meant to measure type. It is first one is dry friction and second one is wet friction. But if I'm not mentioned here Coulomb friction and viscous friction, you haven't that much able to correlate with these terms. So dry friction we call it as Coulomb friction and wet friction we call it as viscous friction. Okay. So in Coulomb friction, I have uh, I already drawn here one diagram, which is this is one surface. Here we kept one mass, solid mass. Then we applied one force, external force. Then some body mass exerted some weight towards gravity. Okay. Then in response, this surface exerts some opposite and equal reaction, which is N. So where we use this? Where we use? Okay, in engineering mechanics. Already I written here. So So dry friction, Coulomb friction, we deal in engineering mechanics, and wet friction, we also call it as viscous friction. So this also we we are going to deal in fluid mechanics. Dry friction has formula we know µs into n. If you can recall it properly, µs into n in which is in engineering mechanics. So in our fluid mechanics, we have to study further for wet friction in detail or viscous friction. So let's just understand what is viscosity. You might be there. There is a might be chance to aware you are aware regarding viscosity. If I put your if I put into your hand what called honey, and if I put one bag of milk, which is more viscous, obviously honey is more viscous. So viscosity is resistance between two adjacent layers. It is simple. It is the resistance between two adjacent layers. That is very simple. Okay. So to further study wet friction or viscous friction, there is one great scientist, Newton, already did some phenomenal job for us. He already gave us one relationship, which is shear stress is directly proportional to du by dy, which is du by dy is nothing but velocity gradient. So viscosity has two types. First one is dynamic viscosity, and second one is kinematic viscosity. So what I just tell you earlier, which is viscosity is nothing but resistance between two adjacent layers. So here I already drew two layers, adjacent layers. So interactive response between two layers. So it generates shear stress. Remember, these two adjacent layers, it has more velocity than its lower layer. Okay. So interactive response between two layers, there is some resistance, there is some exertion, it generates shear stress. So Newton, what Newton says, shear stress is directly proportional to du by dy. If I further zoom it to these layers, so you know the one basic formula, distance equal to speed into time. Yes, distance is equal to speed into time. Let me just focus a little bit more. Okay. Have you ever remembered this distance equal to speed into time? Yes. So nothing else. I just mentioned, or I just refer this formula here only. So here I am what I'm try to do. Here I put one. Here I put u. So here u plus du, and just multiplied by time, which is dt, and distance between these two adjacent layer is dy. So I just made one angular relationship. I just made one angle here over there, and just wrote here difference between these two adjacent layers. So what is du? Difference between two adjacent layers. And then tan theta is equal to, I just put here some values. So tan theta is equal to opposite upon adjacent. So du into d2 by dy. So what comes? Du by dy is equal to d theta by dt. So du by dy already we know it is velocity gradient, but d theta by dt it is new to you. It is known as just is deformation. So what we have come to say right now, velocity gradient is equal to deformation. And what our the great Newton said, shear stress is directly proportional to du by dy, which means to neglect this proportionality sign, okay, or to avoid this proportionality sign, to remove this proportionality sign, you have to put one constant over here. So I already wrote shear stress is exactly shear stress is equal to k into du by dy. You can denote it as mu. So mu is nothing but dynamic viscosity. And if we have to convert it into stress to from stress to shear force, so obviously you have to just multiply with a, or which is, or you can say contact area. So let's just furthermore discuss about dynamic viscosity. Dynamic viscosity has its unit, which is known as Pascal second. Okay, Pascal is nothing but Newton per meter square. Okay, so you can call it as Newton second per meter square, which I wrote here already. So Newton second per meter square, and here is Newton is mentioned, so it is an SI unit. Okay, remember that. And what is CGS unit? Gram per centimeter second. Okay, which we call it also as poise. So you have to remember this one relationship. One poise is equal to 10 raised to minus 1 Newton second per meter square only. Okay. Uh, when you will go to exam and you have to solve one question regarding viscosity and dynamic viscosity, they 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 will not give you as a direct du and dy values. They will give you just velocity value and like values for distance only. So you have to linearization, and if you can remember it well, this relationship our shear stress is equal to mu into du by dy, then you will easily just transform, easily can transform into this linearization, which is shear stress is equal to mu into u by y, which is very simple. Then second one is kinematic viscosity. It is nothing but just remember like it like that. Kinematic viscosity is equal to dynamic viscosity by mass density. Okay, remember these two units. Kinematic viscosity has mk's unit is meter square per second, and cgs unit is centimeter square per second. If we have to convert, if we are going to convert centimeter square per second to meter square per second, you have to multiply by one factor, which is 10 raised to minus 4. So 1 centimeter, or you can call it call it as one poise. So one poise is equal to 10 raised to minus 4 meter square per second. You have to remember this relationship or this conversion. Then we will now study effect of temperature on viscosity. If we rise the temperature or we increase the temperature, then what will be the effect of temperature on viscosity? We are going to study right now. So in case of dynamic viscosity, let's just first take dynamic viscosity. So if I consider liquid case, okay, just imagine if I take mud. or if I take honey, okay, if I put it on a burner, then means you are going to rise temperature, then viscosity must be at downfall, or viscosity will be in decreasing. Okay, why it is happen? Due to just attractive forces. There is two attractive forces, which is cohesive and adhesive. When you rise the temperature, molecules go separated from each other. Till then the molecules are just sitting besides each one, right. But as soon as you got heated that one honey, so then all molecules go separated due to heat, and adhesion arise and cohesion like fallen. So that's why viscosity or dynamic viscosity got decreased. But this this not in the same when it comes to gas. Okay, when you rise the temperature, so there is already separated molecules. Okay, try to understand what I'm saying. Already separated molecules goes to like goes to run like a fear and just collides with each other. And due to this collision, there is a one like messily randomness occurs there. And due to this randomness and collision, there is some obviously energy exertion. So density will goes to increase while you were about to rise temperature, right? So gas there is a vice versa case happens than liquid. So in case of kinematic viscosity, when if I consider first liquid, then already I told you there is one simple formula of kinematic viscosity, which is dynamic viscosity by mass density. Okay, already you have this formula. Okay, so when I rise the temperature, then viscosity have to be decreased. But how why how? Already I quoted here. Okay, so if I rise the temperature, then dynamic viscosity goes decrease. So when dynamic viscosity goes decrease, obviously kinematic viscosity is going to be decreased also. So so if we rise the temperature, then kinematic and dynamic both viscosities are going to be decreased. And when it comes to gas, I have just two equations. I just wanted to prove mathematically. So here I put two equations. Okay. Here I put two equations. First one is kinematic viscosity is equal to dynamic viscosity by mass density, obviously. And second one is gas equation, which is P is equal to rho RT. Okay. So after observing this gas equation, you will notice temperature and density has a relationship which is inversely proportional to each other, right? So if I rise the temperature or if I increase the temperature, then obviously density has to be decreased. Okay, density has to be decreased. And right, and now you just observe this first our formula. If density has to be decreased or density going to be at decreasing, then you have to be seen increase in kinematic viscosity. So what is my moral? If I temperature increase, then density has to be decreased by this equation. And then for sure, if density goes to decrease, then kinematic viscosity have to be at increase. So after that, we are now to come at compressibility, and you have to just do not get confused between that compressibility denotion, which is where we use beta, and beta is directly or sorry inversely proportional to bulk modulus, okay, which is 1 by k. So our fluid itself is a compressible fluid, so you have to study well. What is our bulk modulus formula in our strength of materials? Here I already wrote, which is direct stress divided by volumetric strain, right? But in FM, just transfer this direct stress into change in pressure, and volumetric strain keep remain as it is. So this is the formula for bulk modulus, but you have to come at compressibility. So bulk modulus is inversely proportional to compressibility. So just I exchange denominator and numerator. Okay, and I put it here as beta, which is compressibility formula. Let's just move ahead towards our next topic, which is types of fluids. Okay, so types of fluids comprises into majorly into two parts. First one is Newtonian fluid, those who follows the Newton's law, which is shear stress directly proportional to the du by dy. Okay, and second one is non-Newtonian fluid. So in the case of Newtonian fluid, if you can see clearly, on our y-axis we put shear stress, and on our x-axis, or which we call it also on our basis axis, we put du by dy. So if you can clearly see where I am writing Newtonian fluid, it is very much clear that this line at 45 degree to the x-axis, this is our Newtonian fluid. Okay, those who follows Newton's law, which is already law is in front of you. Okay, but in reality, there is no such any liquid who follows like this, and we call it also a Newtonian fluid, also an ideal fluid, right? So in case of non-Newtonian fluid, if you carefully listen to me what I am trying to say, or what I am trying to convey to you all, so then just follow my pattern, just follow my sequence. Okay, how to remember, it is very simple and it is very like useful to you further, right? So in non-Newtonian fluid, we further divided into, first one is based on shear stress, those fluids who required or who based on shear stress, and second one is who based on time dependency. So let's first discuss about based on shear stress. So what I'm now the teaching to you, just remember these three sequence. First one is shear thickness or shear thickening. Okay, let's just to reduce thickness of my pen. Okay, so first one is shear thickening, second one is shear thinning, and third one is initial shear, because all these are only solely based on shear stress. So what I write here, first one is shear thickening, second one is shear thinning, and third one is initial shear. So for shear thickening, just remember their direct example. The example is sugar solution, okay, and starch. If you just recall, or if you just imagine what a sugar solution is, okay, then you will get my point. Okay, if you get sugar solution, glass of sugar solution into your hand and stir it by other hand, so after you keep stirring, and then it becomes more thickened, okay, than compared to last one, but not in the same case in shear thinning. Okay, if you take one glass of milk, okay, and if you stir like the same way, okay, but here in milk gets more thinner after some time. Okay, so you can if you will imagine it, then you will understand it better. So, and third one is initial shear, what I wrote here, which is example is toothpaste. uh, to come out some toothpaste onto your brush, you have to push it. Okay, you have to push it, that means you have to generate some initial shear, or some initial stress, or some initial pressure to come out of from that tube. Okay, and then I wrote here their respective scientific terms. Shear thickening fluid, we call it as dilatant fluid. Then shear thinning, we call it as pseudoplastic fluid. And then for initial shear, we call it as Bingham plastic fluid. So if you carefully observe this little diagram or little graph, shear thickening, it means it is thickening. Okay, so here I draw one concave. It goes above. Okay, so it is dilatant fluid. Then what is pseudoplastic? It is shear thinning. So it first go upward, and then it falling down. So it is pseudoplastic. Okay, and then you have to apply some initial shear That's why our Bingham plastic fluid graph goes to upward, okay, and it draws a straight line, right? So just carefully observe here. So first one is, this is our Newtonian fluid, our first type, okay. Then this one, this one, from bottom to it goes upward, so it is our dilatant fluid, right? Then it falling down, so it is pseudoplastic. It means it is shear thinning, okay. It is pseudoplastic. And what I told you the examples of it. So for pseudoplastic it is milk, and for dilatant fluid it is sugar solution. Am I right? Yes. And this is Newtonian fluid, which is an ideal fluid. So it is not generally happening. Yes. And this is our Bingham plastic. And what is their example? Which is toothpaste. Or you may give one more example, which is uh, tomato ketchup, right? And then come to here on based on time dependence. Oh, one more thing here is, okay, these A and B are constant, okay. In this formula, if you carefully observe, A and B is like constant, okay. So for shear thickening, B is 0 and N is greater than 1, okay. And for pseudoplastic, B again 0, B again 0, but N is less than 1. And for initial shear, B not equal to 0, because there is some value, there is some, uh, you can call it initial or threshold, threshold stress, okay. So B is not 0, okay, and here N is equal to 1, okay. And let's come to based on time dependency. There is only two types of fluid, which is obviously if we increase the time, okay. So in first one, their according to their viscosity goes down, okay. And if we increase the time, simultaneously if their viscosity goes upwards, then it is called as rheopectic fluid. So if you imagine the ink or a bottle of ink, okay, in old times, there were so many people who use ink pen, so they can relate it better. So after so much of time happens, ink got more thicker, okay. And in case of our pen, if time goes to increase, then their viscosity goes down. So this is called thixotropic. So what is their curve like? So it is going to down, so it is falling down. So that's why I already drawn here. And for rheopectic fluid, the according to time, okay, simultaneously their viscosity is also going increasing too. So their graph keep rising. So here, so below, sorry. So here, this is our rheopectic, right? And what is the example of our rheopectic, which is ink. And here is our thixotropic. What is the example? Pen. So in this manner, what I have already told you in what is this sequence, so you can follow it like this. So first remember their basic criteria for distinguishing, right? First one is based on shear stress. So shear stress is more important, and second one is based on time dependency. So here time is more important. So in case of based on shear stress fluids, so first one is shear thickening, then shear thinning, and then initial shear. So shear thickening, you can remember it first by their example, so you can imagine it better. So shear thickening is like sugar solution and starch, then shear thinning milk, okay. Just imagine one glass of milk or one glass of sugar solution, you put, okay, and by other hand you are stirring like it, so you can imagine it better, you can understand it better. So for initial shear, you have to push it to come forward. So such liquid example is toothpaste or tomato ketchup, right? So according to their respectively, I just gave their name. which is dilatant fluid. Shear thickening fluid is called dilatant fluid. Shear thinning is known as pseudoplastic, and initial shear known as being amplastic. And in case of time dependency fluid, obviously there is only two cases. Time is in both ways. If you gets increasing, okay, then first one is their viscosity. They going to like more viscous or less viscous. So if their viscosity goes downward, then it is called thixotropic fluid, and their example is pent. Okay, and if such fluids there according to time or by the time their viscosity gets increased to, then such liquids we call it as rheopeptic fluid, and their example is ink. So I hope you understand it well, which is types of fluids.